So, I think we're back. Hello and welcome back. Hope you had a good lunch. If you didn't, it's not really our fault this time. I want to give you the quiz answers if we could. These went out on Twitter. We had some good answers here, and some of these more tricky than others. Oscar, can you see this? Do you want to have a guess at any of these? Do you think that first one is?
It's pretty tricky. It's also small. I can barely read it.
Okay, well, don't worry. It's the flag package was the first one. The next one is that's just some binary look. What about this next one? That was a kind of security and a dice. So crypto rand there. This one was hard. There's like some sushi and donuts and things. Somebody did get this on Twitter. The answer is bytes.
Oh.
Yep. The next one is the archive zip. Kind of makes sense. This one was also tricky, but people did get it. That was like a boat sinking and then an atomic. So a little bit cryptic there. That was the sync atomic package from the standard library. The next one, that's an image, and that pencil means draw in this world. There we have it. The next one, number 8, little runner and a clock. That's the runtime package. The next one is a violin, a banjo, and a guitar. So that's, of course, the strings package. And finally, just this little signal emoji there, OS signal. So congratulations for anyone that got those right. You don't win any prizes. But actually, this next talk is going to be quite a cool prize. As Go programmers, we spend a lot of time writing code that runs virtually. It runs in websites or it runs services. It's very special when our code reaches out into the real world, I think. And this next talk is a kind of great example of that. So I want you to please welcome, we'll talk about your charity first. Oscar Söderlund, right?
Yes.
Söderlund. Okay, Oscar. Your charity is the Swedish Heart Lung Foundation. Why did you choose that?
It's partly because they're a very high integrity foundation in Sweden that just funds research. And I've donated to them before. And right now they're funding a lot of corona research. So it feels like a good way to invest.
Nice. Yes. Now, when I was growing up, I was a massive fan of Einride and obviously Herbie. And these were kind of cars that could, they were intelligent cars. They could kind of drive themselves. It's very exciting. This package you're going to talk about enables that for your company, right?
Yeah. It's a library for like talking to vehicles and steering vehicles. Mm-hmm. And I grew up watching Tomorrow Never Dies, James Bond. And I was super impressed with the, controlling the car with the thing. Yeah. And, I don't want to get ahead of myself, but this is going to be really interesting.
I can't wait, and I don't need to because it's time. We're going to now jump into your talk. Okay. I am secretly hoping that there's going to be some crashing involved in this live demo, but that's just me. We'll see. Thanks, Oscar. Take it away.
Thank you, Matt. I'm going to share my slides and get into presentation mode, and then we're going to go. Let's see here. Excellent. Okay. Hi, everyone. My name is Oscar, and I'm from a company called Einride here in Sweden. And I'm going to talk today about the use of Go in driverless vehicles. And that's a big topic. So we're going to narrow down on a specific subject, which is vehicle network communication. And a library that we've developed specifically for that, an open source library for communicating with vehicles that we call CAN Go. CAN is short for Controller Area Network, and it's a common vehicle networking technology. And as you can see, I'm doing this talk from inside a car because I was thinking, now that we're doing it remote, why not do something that we can't do on stage and actually demo this library on a real vehicle? So cross my heart, hope to die. By the end of this talk, we'll be driving this car using Go. Okay. But let's start from the basics. A little bit about me, not too much. I have never worked with vehicles before joining Einride. I consider myself a pretty run-of-the-mill software engineer. My only experience with vehicles is when I used to work as a postman, paying my way through college. And as you can see, like I've experienced firsthand the sort of dangers of driving on the road. And these days I'm working hard at just removing myself from the driver's seat, so to speak. But before we get into detail, let's also talk about Einride and what we're doing, because we're not on a mission to build self-driving vehicles. We're on a mission to develop and deploy sustainable transport. And the sort of core problem that we're trying to solve is the emissions of the transport industry. Transport industry is pretty old and it needs to go electric so that we can get rid of all these emissions. But the transport industry is also pretty resistant to new technology and change. And that's where we're sort of coming in to develop some new ideas and solutions. And one of our main ideas is that to sort of drive this change, we go one step further in the technology roadmap to not just electric vehicles, but autonomous vehicles. And we offer autonomous transport as a commercial service to our customers today. And we found that this makes them really excited and willing to start changing and upgrading themselves. And so we build our own autonomous vehicles. Obviously, we don't do everything inside there. I'm going to go into that. But one of the key things that we do as a company is that we use Go as our primary software development language. And I'm going to tell you more about why that is successful pretty soon. But first, I just want to show you sort of how this looks. I hope you can see that there's a video on the screen. This is from last year when we did our first commercial transport drive. It's just 300 meters transporting tires between two warehouses. But you can see here that our autonomous vehicle has absolutely no driver's cabin. There's no person inside the vehicle. And that's sort of the approach that we're taking as a technology company. We're starting without the person in the vehicle from the beginning and developing all the safety systems that's required to make the vehicle safe. And now I want to go a little bit into detail on how does Go fit into this vehicle and what's inside that at all. So if we look at autonomous vehicles at a high level, you can start breaking them down into a lot of different parts. Like down here, you see the base chassis, for example, and that's what we normally consider an electric truck. And then there's a lot of different areas here where there's sort of leading edge technology coming together to form a coherent system. And you can break these down even further. And even at this level, there's no one, I would say, company that can be or are the experts. So when you want to build a user-facing autonomous vehicles, the primary challenge that you will be facing is integration of all these leading-edge technologies. So if we add some color here, our vehicle is a lot of different technologies that we find on the market, and we work with different vendors, and then we put that together into a coherent system, and we add sort of the missing pieces, which is a lot of glue code, not gonna lie, but also some novel inventions, specifically in the area of safety. And as you can imagine, I use the word glue code, we find that Go is a super successful language to use for integrating different systems together, partly because it's so good at networking, partly because it's so easy to sort of iterate and prototype and do quick solutions. I mean, it's not like we go from top to bottom and find all the different technologies in this vehicle from the start. We're constantly evaluating different things, integrating new solutions into the vehicle, and there being able to use Go has really made us maybe much faster than we would have been using a different programming language. And obviously, this is a networking problem. There are many different types of network in the vehicle, and there are many separate networks. But on a high level, when you're dealing with vehicles, there's two types of networks. There's like the local area networks that we all have come to know and love, that we're all pretty familiar with, like TCP/IP communication. But then there's vehicle-specific networks, where the sort of main one is this technology called CAN, controller area network. And we found that one of the challenges for us using Go was we need to be able to speak to all these technologies that only communicate over CAN. And so that's like one of the main problems that we had to solve pretty early in our journey. Like, how can we get access to all these CAN speaking systems from our Go code? And so that's where we started looking into, like, you know, how can we solve this? And before we go into the specific solution with Go, let me just tell you a little bit about like controller area network technology. I'm not going to go into detail here. There's great material. There's a company in Gothenburg called Quasar who do online video series. It's basically just a repetition of that. So I recommend you just go there and look at it. But like on a super high level, CAN is pretty similar to like Ethernet networking technology that we're already familiar with. But it's built from the ground up to be really cheap and robust and simple. So you basically just take a twisted pair cable and you clip a bunch of computers onto that cable, and then they broadcast data to each other just by sending, you know, high and low electrical signals as bits, and they're synchronized to the same bit rate. And data is transmitted sort of like UDP packets. In this domain, they're called CAN frames. And on the screen here, you see an example of a CAN frame. It has a message ID and a payload. And since I mentioned before, like this is a cost-optimized and robustness-optimized technology. So in the most basic form of this technology, you can only transmit 8 bytes per frame. And these message identifiers can be 11 bits. But there are evolutions of CAN where you can do more. But today, I'm going to speak about the sort of basic one. Like the CAN standard itself doesn't go into detail on how are you supposed to represent your data in these 8-byte payloads. But an industry standard has sort of emerged, a de facto standard from one of the major like CAN technology vendors. And it's a sort of data specification format called DBC, which is short for database for CAN, I think. There's a lot of folklore since there's little public documentation on it. But there's enough information on it to be able to see how it works and build your own parser, and thereby start to integrate with the sort of ecosystem of CAN technologies that's out there. And I mean, the ASCII file format that describes the data representation is probably not meant for human eyes originally, but you can still read it and see it's just very like compactly represented. And what we see here is like a steering command message that's sent to a steering controller to turn the wheels on a vehicle. And there's one field in the message, or one signal as it's called in CAN, the steering angle. And the schema describes how does that get packed into bits, and how does the raw bit value get interpreted as an actual physical steering angle. And this example down here shows for this particular CAN frame, which is a steering command, you interpret it as a signed value, multiply with a scaling factor, and you get the value that we're right now asking the wheels to turn at a minus 8.7 degree angle. So that's basically it. Like, that's CAN. And if you want to communicate with CAN systems from like a Linux system, your best choice, I would say, is to use the SocketCAN kernel module. It's been available ever since 2008 when it was developed by Volkswagen. So this is, I would call it production grade technologies. That's one of the questions I had initially with it. And the general idea is basically to reuse the Linux networking stack and present like a very familiar and easy to work with interface to the CAN bus, where once you're dealing with sockets, it's easy to like add socket compatible technologies on top. And one such socket compatible technology is obviously like Go. Oh yeah, that's right. I want to mention, if you want to get into this stuff and try it out at home or stuff like that, I would say the easiest way is to get a CAN hat for a Raspberry Pi. The Linux, like Raspbian has all the kernel modules to just make that work. You just need to do some soldering probably. But back to like using this from Go, I mean, all you're doing is creating a socket using normal syscalls, and that's easy to do with Go. But there are some specific features that you need to model, like the address of a CAN interface, which wasn't available in the Go runtime until 2016, when it was added by this person, Elliot Morrison Reed. We owe him a great deal, I can say, because as we were coming up with these ideas, like we want to use Go to communicate on the CAN bus, we started looking like, can we actually do this? And we started, going into the source code, and we saw, it's already been added a couple of years ago. So everything was already in place when we sort of came here to do this. And basically, once you've opened a socket to the CAN bus, from the Go runtime, you can wrap it in an OS file, and you have a really simple way of just reading and writing bytes from it. But the idea with SocketCAN is to treat it as much as a network connection as possible. And then, of course, like we would like to just have a very familiar netcon API to it. And there, again, there was some additions that needed to be made to the Go runtime. But it turns out that while we were in the process of exploring this was being added to Go 1.11, the ability to plug the CAN file descriptor and socket into the Go netpoller to make all the asynchronous networking APIs work, like set timeout and like set read timeout, set write timeout. And at the time we started using this in production was basically when this came in with Go 1.11. So ever since then, you've basically been able to use the Go standard library to communicate on the CAN bus. This thing on the right here is like a hello world from the Go standard library to the CAN bus. And as you can see, we only have 8 bytes, so we can only say hi world. But what you're seeing from top to bottom is us looking up a network interface, which the Linux kernel presents the CAN bus as a network interface. Open a socket, bind the socket to that CAN network interface. When we call set non-block is when we make sure that the file descriptor gets registered with the netpoller to make all the asynchronous APIs work. And once we're here, we can just start writing data. And down here, you see the data representation format used by SocketCAN. It's super simple, like 16 bytes. First comes the ID and some flags, and then comes the data length, and then comes the data. So we wanted to do more than just send bytes up and down the socket, obviously. Like we want to take these DVC files that we get from the vendor, and we want to just as quickly as possible get up and running and communicate with all these different systems. So we looked at what libraries were already available, and there's some great stuff already. These two that I link here, we looked at, but we determined that they lacked some functionalities that we really wanted. And at their core, nobody was using a netcon interface to the CAN bus. So we thought, let's see what happens if we start from scratch with a netcon interface and start building stuff on top of it. And we'd already been working a lot with protobuf and gRPC, so we felt like this is a very similar type of problem. We want to create the same developer experience for ourselves with CAN that we have with protobuf and gRPC. So our main goal is just, let's take one of these DVC files and code generate Go structs so that we can, in a type-safe way, generate the messages that we want to send and parse them. And let's also generate high-level APIs so that we don't even need to deal with the network communication ourselves. All that's handled in the background. And that's sort of where we are right now. The library is still pretty rough and fresh, but the rest of this talk, I want to demonstrate some of the functionalities that we ourselves are using right now for like integrating different sensors in the vehicle and also talking to the vehicle itself and controlling different parts of the steering system. So like here's an example of the Hello World case with our library. One function that transmits, and we're using like a dial function to dial the CAN interface and transmit a CAN frame, which we've just created a small Go struct to model it. And on the same end, we looked a little bit at the buff IO scanner and created a similar interface to that, but just reading CAN frames from the CAN bus, and that's been working out great. But that's still a low-level API, and so we built a simple parser for DBC files. You can see here a super small example code for parsing a DBC snippet, which becomes like a sort of an abstract syntax tree, but just a data structure that describes the file. And from that, we can generate code and also do some basic linting to keep all our DBC files in good shape. And here's an example, but this I want to demonstrate in the actual car, so let's not go too much into detail here. This is how it looks when you're using the code generated messages to set a specific value, and or in this case, we're reading from the CAN bus and parsing a known message in a type-safe way. And in this example, we've gone one level up and code generated a full like network interface where we can just say, we are going to act as this node on the CAN bus, and the DBC file will be describing which messages we are sending and at what intervals. So all we need to do is to say, we want to be this node, we want to set this value for this particular signal, and then go. So when we run this example code, we would randomly be blinking with our blinkers every second or so. But now let's use the remainder of our time to just do some live demoing. And one of my colleagues, Trygve, is going to get in the car and be a safety driver for us. This car, by the way, we call Mr. Lang, and it's one of our primary test vehicles. It's been retrofitted with a CAN bus that gives you access to steering interfaces and stuff like that. So like this has already been like pre-built for development. You would not be able to do this stuff with your own car unless you were doing some stuff to it first. But let's go into my code editor here and look at like the first example code. First, we need to bring up the network interface to the vehicle, and we're using the standard IP route tool to do that. You can see that there's a CAN 0 interface. I'm gonna what I'm doing now is just activating the network interface and configuring it with the correct bitrate on the CAN bus, because every node on the CAN bus needs to know what bitrate everyone else is talking on. And there is some basic CAN tooling in the Linux kernel, so we can see if we do CAN dump CAN 0, we can see this is what it looks on the CAN bus. But now let's do this from Go instead. So in this small example code, we're dialing the CAN bus and we're creating a receiver that works like a buff IO scanner. And if we run this example, like we are using Go to read straight from the CAN bus in this car, which I think is pretty cool. And it's pretty easy to generate code from this. Let me check that I'm keeping time. Yes. So this is the actual DBC file that describes the interface to this vehicle. There's messages for braking and getting status on the braking and stuff like that. So what I'm going to do is I'm going to say go run go.einride.tech can. So we've created a small command line utility called CAN tool for like working with CAN. So far, all you can do is generate code and lint DBC files. So if we generate some code from this file into like this folder here. Here we, let's see here. Why does this not work? Here. Sorry about this, but I've prepared this in advance, so we don't need to worry, of course. And what happens when you generate the code is you get a file that looks very much like a generated protobuf file with all the fields for all the messages and so forth, so that you can interact with the messages in a type-safe way. And if we run this example code, and we add in here, like we want to look at what the angle the wheels are at. So we want to parse the steer report message. And we check what ID the CAN frame is, and if it is a steering report message, we parse that CAN frame as a steering report. And let's print the steering angle. Wait, where am I? This is not going exactly as planned because I'm getting lost and the code. Ah, sorry. There we go. But okay, let's move on to the next part because we are. I'm getting lost in my own thoughts here. But that's an example of reading from the CAN bus and parsing. The next example here, we're going to be transmitting data to the actual CAN bus. And as you can see here, we're dialing the CAN bus again. We're creating a transmitter, which just encodes the messages as SocketCAN frames. And we're creating a turn signal command and setting the turn signal to the enum to turn left. All this is specified in the DBC file. And when we send this, we should be blinking to the left. That worked, but let's blink to the right so that we can see in the camera. That should be it. But CAN buses mostly expect your communication to be cyclical. So if we want to keep on blinking, we need cyclical communication. And that's where these higher level APIs, where we're acting as a node on the CAN bus, are useful. So let's instantiate one of these nodes. Like this. And then say turn signal command, we want to enable cyclical transmission on that. And we want to set the turn signal to light. And then basically you run the node. And then this will be transmitting the signal in the background all the time. And if we want to update the signal, we can do that asynchronously by taking a lock. So that's that. Now, let's make a little jump so that we can get more control signals into the system. And to do this, we've developed a simple gamepad library that just reads gamepad input from EVDev. And that's where I'm going to use the Steam controller that I have right here. And this example code basically just reads the input from the controller and prints it out to the terminal. So what you're seeing here on the screen is up to the right. You can see that I'm turning the left stick a little bit and I'm turning the right stick. And every time there's an event emitted from EVDev, we're reading that with the event scanner on the left. So that lets us sort of update the data on the CAN bus as we're getting events from somewhere else. And we use this a lot for debugging, actually. So in this next code example that I have, I've put together a combination of the CAN node that you saw before and the controller input that you saw right now. And we'll be cyclically transmitting a brake command and a steering command, and we'll be using the input from the controller to change the values of those. So we're enabling cyclic transmission on these two messages and starting the CAN node. Then we start a separate Go routine that reads input from the controller. And every time we get an input, we use the left stick to turn the wheels and set the desired steering angle. And we use the right stick to, we use the left trigger to control the brakes. And when we're going at these low speeds, we don't need any throttle of our own, which is also good because then we can't accidentally use the throttle. So I've thought about that. Now, if we run this, we should be seeing that like we're running our CAN node and we're getting input from the controller. And as I turn my steering or like my joystick here, I'm able to turn the wheels. This is just by updating the value that we're sending to the CAN bus. And if you had any hardware and a DBC file, with this amount of effort, you would be able to interact with this stuff as well. And with the left trigger, I'm controlling the brake. So now I'm just gonna ask Trygve to put us into drive gear. And I'm gonna hold down the brakes. And I'm gonna release the brakes slowly. That should actually get us going. Yes. And let's turn a little bit. Let's see if we can go all the way back. So what I'm doing right now is just I'm using the stick to control the wheel, and I'm using the left trigger to control the brakes. And I intentionally left gear shifting out from the example code. So I'm gonna let Trygve gear shift for us. Thank you, Trygve. And here we go again. Backing up a little bit. We have a backing camera, so it's fine. And I think that's fine. And we're back. Sweet. So I'm gonna stop the car here. Thank you, Trygve. And that brings us back to the presentation. That concludes the demo. So where are we right now with this library? We support the basic stuff and we support code generating from the DBC file, but there's a lot of features in SocketCAN that we don't yet support. Specifically, a feature called the Broadcast Manager that can help you transmit these cyclical messages in a more efficient way. And we also don't support the latest standard of CAN yet, CAN-FD, which lets you transmit bigger frames, I think up to 64 bytes. So that's something that as soon as we encounter hardware that we need in our vehicle, that's going to pop up in our library. But if that's something that you need right now and you want to work with us on that, just get in touch. Maybe documentation is a little bit lacking so far, but we're happy to answer any questions that you have and accept pull requests. And if you want to add new features, just submit an issue so we can find out what you're trying to achieve. So far, usage of this library is pretty sparse. We shared this at Go meetups in Gothenburg and Stockholm. And so far, we know of one other company who's using it. And they are a whole 870 meters away from us. So far it has not spread very much, but they're using it to develop software for an electric motorbike. And we're using this library for production usages. And if you want to use it in your project, just get in touch with us and we'd love to talk to you. I'm not very much on Twitter these days, but you can ping me on the Gopher Slack. That's where I hang out. That's it for me. Thank you for listening. And it's great to talk to you today.
Excellent stuff. Really good. What a cool demo. I couldn't believe it when at the end you just drive in the car like GTA.
It's so simple once you're just like, you're getting inputs and you're sending them to the CAN bus. But the feeling that you get when you're controlling something is great.
Yeah, absolutely. Well, okay. Unfortunately, we've run out of time. We don't have time for questions. But if you have any questions or you want to chat more about that, in the sessions section on the side, there's a group networking place where people are hanging out. So maybe you'll catch Oscar in there. Oscar, thanks again. Great job. What a cool demo. We're going to take a quick 5-minute break and we'll be back with our final talk of the day with Roberto Clapis. So we'll see you in 5.
Thank you so much.